You can't call yourself a software engineer unless you understand computational complexity. Computational complexity is a way of measuring how efficient an algorithm is at solving a problem. It's important because it tells us how well the algorithm will scale as the size of the input increases. Let's take a look at the two components that make up the complexity analysis of an algorithm: time and space complexity. Time complexity measures how long an algorithm takes to run as the size of the input increases. It's typically expressed using big O notation, which gives an upper bound on the number of steps the algorithm takes. For example, if an algorithm has a time complexity of O of n, this means that the number of steps it takes grows at most linearly with the size of the input. Space complexity measures how much memory an algorithm uses as the size of the input increases. Like time complexity, it's typically expressed using big O notation. Here are some common time and space complexities. First, we have O of 1, constant time. This means that the number of steps does not depend on the size of the input. Then we have O log of n, logarithmic time, which means that the number of steps grows logarithmically with the size of the input. Then we have O of n, or linear time, O of n, log linear time, O of n squared, quadratic time, and O of n cubed, cubic time. There's also O of 2 of n exponential time, which is the number of steps growing exponentially with the size of the input. It's important to note that these are just rough estimates, and the actual complexity of an algorithm can be affected by various factors, such as the specific input, the hardware being used, and the specific implementation of the algorithm.